The final topic that we're going to look at in root finding is finding the roots of systems of equations. So an important problem that often arises is to locate the roots as a set of n simultaneous equations, and generally speaking these equations will be non-linear. If they were linear we could solve them directly, but generally speaking they're non-linear. We're going to write that system of equations basically as f1, f2 all the way up to fn, and they're going to be functions of variables x1, x2 up to xn. Generally each one of these functions represents an n-1 dimensional surface that's embedded in an n-dimensional space. Now that's a fancy way of saying it's complicated. So the values of xi, where all of these equations are satisfied, and that is if a solution exists, and often it doesn't, these will be a point or perhaps a set of points. Okay, this n-dimensional generic system looks pretty complicated. We're going to look at a simple two-dimensional problem to kind of get the idea across, but it's easily extended to multiple dimensions. So let's consider when a parabola, and the general form for the parabola is y equals ax squared plus bx plus c is equal to 0, and where does this intersect a circle? X minus d squared plus y minus e squared minus r squared is equal to 0. And we're just going to choose an example where a is 2, b is 0, c is minus 3, d and e are 0, and the radius of the circle is 1.5. So that's plotted in the figure on the right hand side, and for these values of the parameters there are actually 4 points where this parabola is equal to the circle, and that's really what we're trying to find. Those 4 points there. So in terms of the general system of equations that we wrote earlier, we've got a rather simpler system. We only have n is equal to 2 here, and the functions are f1, and we're going to say they're functions of x and y. So f1 is equal to y minus ax squared minus bx minus c, and that's got to be equal to 0. And f2 is the circle, and that's given by x minus d squared plus y minus e squared minus r squared is equal to 0. So those are our 2 functions. And to simplify, just so that mathematics looks a little bit easier, we're going to let f1 equal f of xy and f2 equal to g of xy. So we're going to use f and g instead of f1 and f2, and so really the system of equations can now be written as f of xy is equal to 0 and g of xy is equal to 0. And we're trying to find what values of x and y these are both satisfied at simultaneously. So our 2 functions f and g, each of these can be written using two-dimensional Taylor series. So let's imagine we know the function value at a point xi, yi, and we want to know what the function value is at some neighbouring point, xi plus delta x, yi plus delta y. And so we can expand that in a two-dimensional Taylor series. So the left-hand side value here is equal to the function value at xi, yi plus delta x times the partial derivative of f with respect to x plus delta y times the partial derivative of f with respect to y plus some higher order terms. And we're going to neglect those higher order terms as usual. Likewise, we can write the Taylor series, two-dimensional Taylor series for g of xi plus delta x and yi plus delta y in a similar form. So we've got these 2 equations here. We're going to ignore the higher order terms, so we're going to get rid of those. So that will then leave us with this system of equations here. Okay, so if xi, yi is our current guess for one of the roots of both of these equations, what we're trying to do is we're trying to find a new point, xi plus 1, which is equal to xi plus delta x. We don't know what delta x is. yi plus 1 is equal to yi plus delta y. So we're trying to find 2 points where these are both equal to 0. So the problem is reformulated by saying we're aiming to find delta x and delta y such that f of xi plus 1, yi plus 1 is equal to 0, and g of xi plus 1, yi plus 1 is equal to 0. And we do that by finding these two increments, delta x and delta y. So take this set of equations here, say we want these two terms to be equal to 0, and that gives us then these two equations here. Now, this is only a linear system. We know that in reality there are higher order terms here that will make a difference. So even if we can solve this, it doesn't mean we've hit the answer, it only means we've approximately hit the answer. So, if we move that term to the left-hand side, we can easily write this term here in the following form. That is a matrix equation A, x is equal to b, where the matrix A is given by this set of derivatives. The unknown vector x is the delta x, delta y increment, and the right-hand side are negative the function values. This looks very, very similar to the Newton-Raphson method, except now it's a matrix equation. I is the iteration number. So let's rewrite our Newton-Raphson problem for this simple two-dimensional case. It's actually quite easy. We just write the inverse of this matrix here. So our x is equal to a to the minus 1 times b. And we can actually calculate this matrix inverse for a 2 by 2 system quite simply, quite efficiently. So the process is iteratively. So we start off, we start off with an estimate xi, yi. We solve this equation on the right-hand side up here, and we obtain new values of the increment delta x and delta y. We then update our next guesses. So we say xi is equal to xi plus delta x, and yi is equal to yi plus delta y. That's our new guess for the root. We then reevaluate the function values and the derivatives. So we have to reevaluate the f and the g. We need to reevaluate all of these derivatives. And we repeat this process until delta x and delta y are very small, and or the function values on the right-hand side are both less than some tolerance that we're prepared to accept. So on convergence then, we have approximated the value where these two functions are equal. Now, in the case that we looked at before with the parabola and the circle, this process will only find one of those roots, and the root that we find will depend on where we start. So this process, this generalized Newton-Raphson process, isn't guaranteed to find all of the roots. You need to be pretty clever and pretty exhaustive in your searching to make sure you've got all of them. The drawbacks of this in multi-dimensions, imagine we have 10 functions and 10 variables. We have to write function files for all of the derivatives as well as the functions. So if there's 10 dimensions, that's 10 derivatives for each function. That in total equals 110 function files. The other thing is, generally we have to be pretty close to the solution in order for this method to converge. So modifications to the method, well, clearly using Newton-Raphson is problematic. We could use the equivalent of the secant method. So that way we don't need to worry about the derivative functions, we can just calculate these things numerically. There are also a number of public domain routines that are available to do this, and you can have a look at numerical recipes. We're not going to focus on this in this unit, but it is something that you might need to use in the computer labs. So, the last 4 videos are focused on root finding, and the key points that we need to worry about are, first of all, for one-dimensional functions, there are 2 key methods, bracketed methods. The 2 methods that we looked at share algorithmic similarity. The only thing that changes is the way in which you make your next guess. The other class of methods are known as open methods. They're based on finding the intersection of the tangent to the function with the x-axis. And again, the 3 methods that we looked at share algorithmic similarity, and you need to know the underlying concept. The formulas are not important. You can derive them. And finally, for For multidimensional root finding, you need to use some kind of open method. There's no such thing as a bracketed method when you move into multiple dimensions. And the problem here becomes writing the matrix that you then need to invert. So sometimes it's difficult to write the matrix. Other times, if you have lots of function, it actually becomes quite expensive to invert. So, next set of recordings, we're going to be moving on to interpolation in one dimension.